All right, 9:45. Let's get started. Lord, thank you for bringing us together this morning. Thank you for everything that you do for us. I pray that you would continue to give us what we need to be successful this semester. Help us to get through all of the things that we need to do to get done this week and have a great weekend. In your name we pray. Amen. I know, praying for the weekend already, and it's only Tuesday. What? What are we doing today? Right. First of all, can you guys at home hear me? Because I had a significant upgrade on hardware, and so this is different than the face shield that I've been normally wearing. Now I have riot gear because we were going to be talking about exam stuff, right? And I just want to make sure I don't get overwhelmed. All right. It was a joke. What was it really? We'll find out. All right. So I'm going to assume that people can hear me. Very good. It's a friendly reminder that if you are at home and watching and not in the room, your camera should be on, right? Friendly reminder. All right. So, what are we doing today, right? So we're going to recap a little bit, and then we're talking about block diagrams today. This is going to be the final mathematical model representation that we're going to talk about. And then finally, we'll get into some differential equations, right? And for those of you who didn't check Discord or are not on Discord, we are going to do some group work at some point today. So we're going to need a laptop, right, if you're in class. All right. Linearization. Sure. What are we trying to do? We're trying to make something that's nonlinear linear. Okay. And if we're trying to make something nonlinear linear, what does the idea of linearization deal with, right? It deals with actually making a line, right? So what we're trying to do is we are trying to make a line that passes through a specific point on our original function that we know is nonlinear, that is now an estimate, right? And that straight line will be good to a certain point over a certain range, right? And then after some time, it decays and it goes away, right? We're going to watch a video in a second to recap linearization. So if you still have questions after that, then we can get more into it, right? Laplace transfer functions. Well, we're not there yet. We talked about time domain transfer functions, right? And the idea of a transfer function. The idea of a transfer function, right? The idea of a transfer function is that we can create some ratio of our output to our input, right? Y of s over u of s, right? And this is going to become clear why we want to do this later. In the time domain, we don't really use it very much. It's really more so used for Laplace domain type calculations, right? And so specifically, if you wanted the output of a function and you had the Laplace transform transfer function of it, be able to do that very easily using algebra and inverse Laplace transform, right? Which we will talk about. We're just not there yet. But we talked about it in terms of the time domain. And the reason that we did is because we are going to talk about block diagrams today. And block diagrams run on transfer functions. Okay, and that's the reason why we talked about it. So let's maybe watch this. Yeah, we'll watch this.
Let's say that we're interested in approximating what the square root of 4.36 is equal to. So we want to figure out an approximation of this, and we don't have a calculator at hand. Well, one way to think about it is we know what the square root of 4 is. We know that this is positive 2. The principal root of 4 is positive 2. So you say, okay, this is going to be a little bit more than 2. But let's say that we want to get a little bit more accurate. And so what I'm going to show you in this video is a method for doing that, for approximating the value of a function near a value where we already know the value. So what am I talking about? So let's just imagine that we had the function we have the function f of x is equal to the square root of x, which is, of course, the same thing as x to the 1/2 power. So we know what f of 2 is. We know that f of 2, or sorry, we know that f of 4 is. We know that f of 4 is the square root of 4, which is going to be equal to 2, or the principal root of 4, which is equal to positive 2. And what we want to approximate, we want to figure out what f of 4.36 is equal to. This is just another way of framing the exact same question that we started off this video. So let's just imagine our function. Let's just imagine it for a second. So let me draw some axes. This is my y-axis. This is my x-axis. And let's graph y is equal to f of x. So let's say it looks something like this. Y equals f of x looks something like that. So that's pretty decent. All right, so that right there is y is equal to f of x. And we know f of 4 is equal to 2. F of 4 is equal to 2. So this is when x is equal to 4. I haven't drawn it really to scale, but hopefully this is clear enough. So that right over here is going to be 2. That's f of 4. And what we want to approximate is f of 4.36. So 4.36 might be right around there. And so we want to approximate this y value right over here. We want to approximate that right over here is f of 4.36. And once again, we're assuming we don't have a calculator at hand. So how can we do that using what we know about derivatives? Well, what if we were to figure out an equation for the line that is tangent to the point, tangent to this point right over here? So the equation of the tangent line at x is equal to 4. And then we use that linearization to approximate values local to it. And this technique is called local linearization. So what I'm saying is, let's figure out what the equation of this line is. Let's call that L of x. And then we can use that and then we can evaluate that at 4.36. And hopefully that'll be a little bit easier to do than to try to figure out this right over here. So how would we do that? Well, one way to think about it, obviously there's many ways to express a line, but one way to think about it is, okay, L of x is going to be, it's going to be f of 4. It's going to be f of 4, which is 2. It's going to be f of 4 plus the slope at x equals 4, which is, of course, the derivative, f prime of 4. So that's going to be the slope of this line of L of x is f prime of 4. Let me make that clear. So this right over here is the slope when x is at x equals 4. So it's the slope of this entire line. And so any other point on this, it's going to be f of 4 plus the slope times how far you are away from x equals 4. So it's going to be times x minus 4. Let's just validate that this makes sense. When we put 4.36 here, actually let me zoom in on this graph just to make things a little bit clearer. So if this is, so I'm going to do a zoom in. I'm going to try to zoom in into this region right over here. So this is the point 4 comma f of 4. And we are going to graph L of x. So let me do that. So this right over here is L of x. That's L of x. And let's say this right over here is the point 4.36 comma f of 4.36. And the way we're going to approximate this value is to figure out what this value is right over here. And what is this one going to be? This right over here is going to be 4.36 comma L of 4.36. This line evaluated when x is equal to 4.36. And what is that going to be? What is that going to be equal to? Well, let's see. Let's just evaluate it. L of 4.36 is going to be f of 4. So it's going to be 2 plus the derivative. So the slope of this line plus f prime of 4 times x minus 4. So 4.36 minus 4 is going to be times 0.36. And that makes sense. You're starting at 2, and you're saying, okay, my change in x is 4.36. So my change in y is going to be my slope times that change in x to get me that value, to get you that value right over there. So let's figure out what this thing actually is. So to do that, we need to figure out f prime of 4. So let's go back up here. I'll leave this little visualization here. So let's see, f prime of x is going to be 1/2 x to the negative 1/2, just using the power rule over here. So f prime of 4 is equal to 1/2 times 4 to the negative 1/2, which is, of course, equal to 1/2 times 1/2. 4 to the 1/2 would be 2. 4 to the negative 1/2 is going to be 1/2. So this is equal to 1/4. So L of, we deserve a little bit of a drum roll now, L of 4.36 is equal to f of 4. It's equal to f of 4, which is, let me just rewrite it. It's f of 4 plus f prime of 4 plus, gee, why am I switching to that color? Let me do the yellow. Plus f prime of 4 times 4.36. Let me make this actually in a new color just so we see it. So 4.36. So times 4.36 minus 4. Minus 4. And actually, let me make all the 4s one color too. So you see it's the same. So just like that. So what is this going to be? Well, this we already established is positive 2. This we already established. Let me do this in the yellow color. This we already established is 1/4. And this part right over here is 0.36. So this is going to be equal to 2 plus 1/4 times 0.36 is 0.9 or 0.09. So this is going to be equal to 2.09. So that is our approximation, and it should be, at least based on how I graphed it, a little bit higher than the actual value of the square root of 4.36. But we could write that up here. This is going to be approximately, let me just write it this way. The square root, I'll just write down here. So we could say the square root of 4.36, which is the same thing as f of 4.36. This is approximately equal to 2.09. Now, let's just say we happen to find a calculator, and just out of curiosity, let's see how good of an approximation this actually is. Let's get a calculator out. And so we want to do the square root of 4.36, and we get 2.088. So we actually, if we round to the nearest hundredths, we got a pretty good approximation. And just like we saw in this indicative graph right over here, our approximation was indeed a little bit higher than the actual value.
All right. So, all right. Basically the same example that we did in class with the nonlinear resistance, right? With the pressure, except that we were running at like 400 kPa and whatever the volumetric flow rate was, right? But it's still that square root approximation, right? So what are we doing? Right, what are we doing? We're either using our Taylor series expansion to create our linearization, or just make the equation of a line that passes through that point, right? What do you need to know, right, if you're going to do that, right? What do we need to know? Well, remember, all of this comes from the slope is the change in y divided by the change in x, right? So if you rearrange this, and I'll write it up here in red, delta y is equal to m times delta x. What is delta y, right? What is delta y? Well, delta y is where I want to be versus where, right? It's where I'm taking my reference at minus where I'm taking my reference at minus my actual y value. Right? No, it's like the opposite. Y minus y star. Right? So I'm running out of room here because I made the video today. Y minus y star is equal to m times x minus x star. All right, which brings us to this equation, which is going to tell us that y is equal to m times x minus x star plus y star, or as you probably know it, y is equal to mx plus b, right? Making the equation of y. So if you're given a function or a part of your function, right, that you know is nonlinear, right? If you're given a nonlinear elements equation, if you're given like a nonlinear string, if you're given a nonlinear resistance, whatever it happens to be, you can take that, you can linearize that element, and then you can throw that into your reduction, and now you have linearized it, and it is now a linear system, right? You can take whatever makes it nonlinear and linearize it about some point. How do you know what point to use, right? That was a question that came up on Thursday last week in one of my classes. Well, typically in the real world, you'll understand what the operating conditions of your system are, right? In the real world, you'll know I'm going to run this between this pressure and this pressure. I'm going to have an input force between here and here, right? I'm planning on my resistance being somewhere in this range, right? So you know over what range you are expecting this to work. So typically you'll pick a value in the middle of that range and see how good you can get on either side, right? That's typically how we would do it. You guys have any other questions on linearization? No? I changed all the dates. I'm pretty sure I changed them in LoudCloud too. I think I did. Either I did or it was a dream that was really vivid where I changed them in LoudCloud, which is really sad kind of that I had a dream about that. But anyway, these are the dates now, right? Homework 4 due on the 8th, lab 2 on the 15th, homework 5 on the 22nd, exam 2 on the 24th. I haven't posted homework 4 yet. I'll post it this week. Trying to get through homework 3 right now. Yeah, Sean. Yes. So the question was, was it intended to have the exam the Tuesday before Thanksgiving? The answer is yes. There's a couple of reasons, right? You don't have to be in the class to do that. So if you have travel plans, right, you should get to wherever you need to be, hopefully before the time you take the exam, right? Or at least be in a McDonald's that has nice enough Wi-Fi, one or the other. Yeah, for 2.5 hours. McDonald's won't kick you out, guys. I promise. They won't. Funny enough, I actually, when I was applying for jobs, I would go sit at a Denny's all day and steal their Wi-Fi and apply for jobs. So a little bit about me. So yeah, so that's the idea. Plus, then we don't have to worry about. Well, then I don't have to worry. That's very selfish. I don't have to worry about giving you guys the same lecture both before and after Thanksgiving, right? And so homework 5 will be due the Sunday before. I'll post the answers, right? I'll post solutions for that right after it's due, so you'll get them on that Monday, and you can use that to help you study the homework 5 stuff. Homework 5 is centered on the Laplace transform, mainly. Okay? Yeah. All right, here are the latest and greatest TriQuizzer standings, right? We've got the life livers and a tie for second in the bag, and Dr. D's sanitizers. Yikes, SDCK, static waffles, 185.3 Zoom engineers. Michael Scott paper, blank, zero division, Quizzard lizards, Matilda's pointy compass, Warzone, doctors without doctors, and just one. That's where we're at. That calculates everything. It's up to date with our exam standings, right? Speaking of the exam. All right, the in-person class. You guys got a 62.63 average with a standard deviation of 11.45%. The TOS class, 58.44% with a standard deviation of 14.8. Historically, this exam is typically high 60s to low 70s as an average. So we're a bit lower. I'm not really pleased by this. So here's a couple of suggestions. Right? Typically, students who have greater success in the class tend to come to office hours more often than not. Okay. If you haven't been coming to office hours, please come to office hours. Right. Well, Dr. Lee, I don't really have any questions. Well, I beg to differ. I beg to differ. I think that there are questions. Typically, what happens, or at least what happened last year, was I would have students just sit in my office and they would either work in there, and if there were too many, they would get a study room, they'd all work together, right? And then they would come back and ask questions as they got stuck. I'm fine with that. I'm fine if you want to sit there and ask questions. Start your homeworks earlier, right? Start assignments earlier. So you have time to ask questions. So it's not Sunday night and you can't get them answered. Okay? What problem did you guys do best on? In-person class, rack and pinion. You guys were solid on that. TOS, you guys rock the op-amp problem. Dante, I'll be posting the homework this week. Hopefully today, maybe tomorrow. You guys rock the op-amp problem. What did you guys do worse on? Both classes, double pendulum for you guys for a double pendulum. Okay. What's going to happen, right? The next exam is coming. Remember, the main thrust of that exam is the stuff that we are learning now. Homework 4 and homework 5. But remember, that is all contingent on the stuff that we learned from modeling, right? So it's not out of the realm of possibility for me to say, model this system and tell me what the response is to a step input, right? Sean. Trying to remember. I think they're about the same size. I didn't try to like make them super long. They're roughly around the same size. The question was, are homeworks 4 and 5 much longer? Not really. Not in terms of the number of problems. Let's put it that way. Some of them might take a little bit longer just because there's now the modeling portion and the additional part of having to look at what the response is telling us, which we haven't really covered yet. Okay. I will deliver I will tie up our story on Friday, right? I'll give you the result of what our conversation with Dr. Q let us. Remember, I'm also running a Dungeons and Dragons game here with you guys. No. Question was, do I think that some of the lowness in scores comes from the blended nature, the broadcast learning, right? The modality, it's hard to say. I think for some people, maybe, because I also have had, I know Professor Price's classes all ended up in the typical average range, like high 60s, low 70s. My 1230 class also ended up in mid 70s as an average. I'm not discounting it for sure. I do think that different people have different learning styles, and that does play a role. We're doing our best. I know everybody's doing their best. But again, like I say every Thursday, right? If you guys are struggling, if you're having problems, and you don't let me know, I can't help you, right? I said this at the beginning of the semester. I want everybody to succeed. I want everybody to do well, but don't mistake that for you're just gonna get a grade, right? The analogy I've used in the past is I'm not Santa Claus, right? I'm not wearing a red suit. You earn your grades, right? So I would urge you very much, everybody, to. I know everybody's got hectic schedules and we've got a lot of stuff to do, and I'm not the only class that you're taking. I get all of that. Try to budget a little bit more time in advance for assignments, so just so that it's not even more time, just start them earlier so you have the time to ask questions, right? If you were to spread it out over the entire course of when the homework is due, it would take you the same amount of time that it would to do it all in one day, right? You're just doing less work at a time, and you're hopefully, if you're struggling, then you have the ability to correct that, right? And that's I think the course of action, right? All right. Any other questions before we actually get into block diagrams? I think you guys will like block diagrams. Sean, so. What is the Tri-Quizzard tournament for, is the question. It is GC's premier academic tournament because it is the only one of its kind that I'm aware of. So by default, makes it the best. The winning team gets a trophy at the end of the semester, and you will become, dare I say, you become immortal in all of the presentations, the first day presentations when I show you a picture of the team. But you'll have to stand 6 feet apart for this one. So mostly fun, I would say mostly fun, just to make things interesting. Hoping that you guys would band together to study in your groups and things like that. Maybe give you a study group if you didn't already have one. Okay. All right, so let's do it. Let's talk about block diagrams. And what is a block diagram? So anybody who has ever looked under the hood of Simulink, well, not even under the hood, just looked at Simulink, right? If you've used Simulink, you've done a block diagram. If you use LabVIEW, you've essentially used a block diagram. It's a little bit different than that. But it is a graphical representation of an interconnected system, right? So it is a way for us to graphically represent our mathematical models. Why do we care? Because Simulink and LabVIEW, right? That is why we care, right? Also, block diagrams are a nice way for us to visualize how all of our signals interact with one another and whether we have feedback between different components. It's really nice for a controls model. How does it work? Each component is a block, usually a transfer function. And when I say usually, I mean like 99% of the time. Simulink will let you use a state space representation as a block if you want. Pros and cons, we'll talk about them later. Blocks are connected by signal paths. So essentially you have a block, right? The block represents, let's talk about the rack and pinion, right? One would represent the rack, one would represent the pinion, and they would be interconnected by something, right? By that contact force that goes back and forth between the two, right? So what are the signals? Signals, we like to think of them as electrical signals, but it's really any output from one block that goes into the next block, right? And we've seen this in the way that we've been doing our models, right? With our input-output models, when we have multiple subsystems or like an electromechanical system, we have some output from the electrical system that goes into, right? This is the idea of our local inputs and outputs, right? Our local inputs and outputs. Signal flow into a block represents a math operation, usually multiplication. So if you have, we'll go over the standard types right in a second. So, all right, so what are we doing? We're making essentially a graphical depiction of our equations, right? Of our mathematical model. To what end? Because in a program like Simulink, you can pull off whatever signal you want and run it to a scope, right? So what do these blocks look like? Well, we've got multiplication by a constant, which we're going to call a gain, right? And here it is at the top, right here, right? Here's my gain block. This is what it looks like. These are the standard Simulink notations for such blocks. Once you start filling them in Simulink, it will actually show you, like if you have a gain of 5, that block will just show you a 5, right? It'll just give you the straight multiplicative index. So we have some input signal, it gets multiplied by k, and we get our output signal y, which is just equal to u times k, or k times u. Okay. We can also do integration, right? So you get an integral block. And there's 3 ways that this can be represented, right? It's either the integrand. Right? So I run my signal in, it gets run through an integrator, and the output is the integral of my input, right? If we're running it in a transfer function mode, 1 over d or 1 over s is what an integral looks like. Still do that? Are these just examples, or do you need to know them off the top of your head? We'll get to the point where you're just going to know them because we use them very often. But if you were actually using Simulink and you needed an integrator, I would recommend opening your library of blocks and typing integrator. Or you don't even have to do that. If you just click in the workspace and start typing, it'll start throwing things up there as suggestions. So if you know you need an integrator, right, just type integrator. If we're drawing them by hand, right, just doing an integral sign inside of a block is sufficient, right? Okay, our dynamic system is represented by a transfer function. We'll call it G of S. This is going to be our plant transfer function in most cases, right? When we say it's a plant, it's whatever our base system is that we're interested in discussing, right? So notice I'll have some input signal go into my transfer function. And if I multiply my transfer function times my input signal, I'll get my output signal. Well, remember, transfer function is what? This, right? So another way of thinking about this is that I've got y of s over u of s, or of t, in this block, right? And if I throw my input signal in there and I multiply them, well, that's output. So you're telling them my transfer function times some input is equal to my output. The transfer function multiplied by the Laplace transform of the input is equal to the output, which is going to be very powerful for us later, but not for right now. Okay. I've already taken care of my typo in there for the next part. So let's talk about this as an example, right? I've got this transfer function, G of S. G of S is 3s plus 2 over s squared plus 4s plus 12. Right, so if I wanted the corresponding input-output equation, right, it wouldn't be 20, it would be y double dot plus 4y dot plus 12y is equal to 3u dot plus 2u, right? What did I do? Remember, right, equal to that. And if I wanted to put this to the time domain, I can use my time domain variables, right? My D operator. Use my D operator. Man, this camera does not want to stay on today, guys. No, okay, whatever. That's cool, I guess. Okay. So we get something like this here, right? Yeah, Sean. So the question is, would it be common to have one of your input variables be an integer? And the answer is, it depends. It depends. It depends on what type of input you have. Typically, we'll go over different types of inputs at the end of class today and what they mean. So think of that more of a forcing function than anything else. Now, if you had a step function in the Laplace domain, yeah, you just end up with an integer. But we'll talk more about that. All right, so if you take this, you cross multiply, right, and you substitute in ddt for your d operator, right, you'll get 4 double prime, 4 double prime, 4 double dot, 4, one more time, y double dot plus 4y dot plus 12y is equal to 3u dot plus 2u, right? So differentiation in the time domain, we multiply by d, and integration, we divide by d, right? That's how we roll. So if we're given a transfer function, right, we should be able to go back and forth between transfer function and the original differential equation that we had, right? No problem. All right. We also have summing junctions. Now sometimes these look like squares. How can you tell it's a summing junction? Well, you see the plus and minus there. That's how you can tell. All right, so what is this one specifically telling me? Well, a summing junction can add or subtract signals together. So you'll notice right here and right here, I've got sign notation here, right? So what is this telling me? This is telling me that U minus W is equal to my output signal Y. So, right, look, you have something coming out. So think of this kind of like a current node, right? Think of this kind of like a current node. You're going to add the things that are coming in and they're going to equal whatever is coming out, right? So I've got a negative signal coming in. I've got a positive signal coming in. When I add those two together, it's U plus negative W or U minus W. It says here that signs must be provided at the summing junction. The general rule of thumb is if you don't provide a sign, that you meant it to be positive. So you'll often see me just mark where my negatives are, right? That's how I was taught to do it. Either way is fine. But remember, if you leave one off, I'm gonna assume automatically that you meant it to be positive. Yeah, that's what I'm gonna assume automatically. All right, you guys have any questions on summing junction? No, pretty. Yeah, so how do we use all these things together, right? That seems important. That seems important. Well, let's do this one. I'll walk us through this one, right? So hey, I don't have to come up with the model. I already have it. Right? This is my DC motor model. And we came up with this model before, right? We did this problem a few weeks ago. Right, I've got two coupled linear first order ODEs here, right? Where I know what all of my variables mean. So how do I do this, right? Well, we did the hard part. We did the time consuming part. He said, even though we've never done this before, nobody knows what to do there. So all right, so there's two ways, right? There's two ways that we can do this. Okay. There's two ways that we can do this. I'll show you guys both ways. You can pick whichever way you like, unless you specifically need something out there, right? So the first way that we can do this is we can do this as two separate systems. We can draw a block diagram for the electrical subsystem and one for the mechanical subsystem. Okay. So think about each of these equations describes their own system. Each one is a subsystem of the entire system, right? So if we did that, what would we want? Well, we're going to need transfer functions, right? Because I told you that what goes in the block is a transfer function, right? So I'm going to need to create a transfer function for each case here. Okay. So let's start with the motor, the armature, right? Remember, I'm going to go back for a second so you can all look. Freeze that. All right, so I've got L I dot, right? Well, I dot is just D I sub L, right? Plus R times I sub L, no D, is equal to E in minus K B times omega. So remember, I want the transfer function, right? I want the transfer function. I didn't really talk about inputs and outputs, right? Yet. I didn't talk about inputs and outputs. How do I make this a transfer function? Well, the way that we've written this, we already have our inputs on one side and our outputs on the other, right? We have our inputs on one side and our outputs on the other. So if I wanted, right, I'm going to say, well, let's do it this way. I've got two inputs. All right, what was the question? That's my differential operator. Remember? D is equal to ddt. Right, so instead of having I dot, I've converted this into I'm going to make a time domain transfer function, right? It's d dt. Okay. So what do I need? Well, remember, I'm trying to make, if it's a transfer function, I need y of t over u of t, right? Okay. So I need the ILs. IL is going to stay here. That's my y of t. U of t is En minus kb omega. And that's going to equal 1 over L d plus R. That's my transfer function. 1 over L d plus R for this particular block. One. Remember, this has two inputs. So both of those have to be on the left-hand side, right? Remember, we're making this ratio, right? Making this ratio. So what did I do? Right? Let's just step it. Right? I'm just saying that in this case, we know that y of t is equal to I sub L, u1 is equal to En, and u2 is equal to kb omega. So u total, we're going to say, is En minus kb omega. That's what we're going to say. Okay, so this is equal to u sub t, right, of t. U total of time. So then, this is equal to that. Okay. So we created this transfer function. 1 over L d plus R. It's our time domain transfer function, right? We also need one for the mechanical side. All right, so we need one for the mechanical side, right? Look at it. JW dot plus B, JW dot. Oh my goodness. J omega dot plus B omega is equal to KM. So same deal here, right? We've got a U1 and U2 here as well. Right. So we're going to treat this entire thing as our input. So if we do this, JD omega plus B omega is equal to Km IL minus TL, right? So my transfer function becomes this. So I'm going to circle that. So I've got two transfer functions, right? Got two transfer functions. So what do we do with this information, right? Well, we can draw a block diagram. How, right? Okay. All right. So let's start with our first equation here, our first transfer function, right? 1 over LD plus R. All right. 1 over LD plus R. Inside of my block, right? That's what I've got. We know we have our input is En minus KB omega, right? That was our input. How do we know that? It's right here. This is our input. Remember, what is the transfer function? What are we saying? We're saying our input function is going into our transfer function block, and we will get y of t out, right? Or another way of thinking about this, right? If I take the transfer function, I can say, well, I sub L has to equal my transfer function. I don't feel like rewriting it right now, right? But the stuff that's in this block here. And that is going to be multiplied by En minus KB omega, right? So how do I get those two signals to be En minus KB omega, right? Well, I've got to take my, come on, PowerPoint. I've got to put a summing junction, right? Because I have some input in here. What do I have? I've got En and KB omega. Right? What does that give me out? I sub L. Well, that is very interesting, he says, and no one believes him. But it is. It is. I'll posit to you. Why would he say that that's interesting? Well, let's look at our next equation, right? Our next transfer function. Well, for this, my output is omega, and that has to equal my transfer function, which I'm abbreviating as TF, right? Which is just this one, times Km IL minus TL. Interesting. Interesting. He said it again. Well, we figured out what IL is, right? So if we run IL through a gain block of K sub M, which is a constant that is specific to our motor, right? Then we have Km IL. That has to go into, oh no. I'm going to move that for a second. This then has to go into a summing junction where we have our load torque coming in that we're subtracting off, right? Where's the load torque coming from? The load torque is whatever we have our system connected to, right? It is the inherent torque that is on the motor to start with. So it is an external load that we're putting on here, right? Km minus TL, that goes in to my transfer function, which is 1 over J D plus B. And what's that going to spit out? Omega. But hey, check this out. This is the same omega that comes back in here that we're just going to multiply by KB. And this, ladies and gentlemen, is the first time that we've drawn a feedback system. Right? We are taking an output signal and we are feeding it back into our system, right? Feeding it back into our system. Now, the advantages of doing your model in this way are really that you can pick off any of these intermediate signals and test them, right? So if you wanted just I sub L, right, you can kick off this into a scope in Simulink, right? You can watch how that changes with time. What if you wanted to know, what this input was, right? You can scope it, right? You can scope this. You literally put a scope wherever you want. So the second method, right, is instead of leaving these as separate systems, we're going to make one giant equation for the overall master system, right? One system-wide equation. Right. So if we do this as a system-wide equation, we're going to get one transfer function in terms of En and omega, right? I have En and I have omega. So how are we going to make that? How are we going to make that happen? Yeah. Hopefully, I gave myself another slide. I'm going to double check it real quick. I did. Perfect. Just one more though. So we'll start it here. Before we move on, does anybody have any questions on this so far? Everybody following and doing all right? I'm going to assume that if you are not telling me that we're not doing all right, that means that you are in fact doing all right.
It's pretty heavy to
Okay.
follow. I almost would like to redo everything we've done to kind of lock it in, but I know you've got to keep going.
We're gonna have there's more examples, right? We got more stuff coming. Okay. So we're gonna do this as a system-wide thing, right? So that means we need a single transfer function. Right, so remember my equations looked like this, right? LDR I sub L plus K B omega is equal to E N and JD plus B times omega is equal to K M I L minus T sub L. So I can do this one of two ways, right? I either have to solve everything for omega or everything for I sub L, since those are the two variables that couple my system. But I told you that I want a relationship between E sub N and omega, so I should probably solve the bottom equation for I sub L, or I mean, it doesn't matter. You can solve either one for I sub L and plug it into the other, right? So I'm going to solve this bottom equation for I sub L. If I solve this for I sub L, I'll get something that looks like this. Why would you leave it like that, Dr. DM? Reasons that we'll talk about later. Doesn't matter. Algebraically, it's the same as combining everything, right? Okay. So I'm going to take this, right? I'm going to take this equation for I sub L and I'm going to plug it into the other equation, right? So we'll end up with a really gross looking right? So this is the reason why I left them separate. right? The reason I left them separate is so I can have all my omega terms together, right? And all of my non-omega terms together. Right? That's why I did it the way I did. Okay, so you can do this a couple ways still, right? You can either get the common denominator, right? You can multiply KB over omega by KM over KM, right? And then add the two things together, which is gross. But I do want you to notice one thing before we do anything else here. These were both first order differential equations when we started, right? They were both first order differential equations when we started. Notice what's going to happen here in this red bracketed area. When, excuse me, when you multiply this through, you're going to get a d squared, right? That's what d squared is. We've created a second order system now, right? Which is what we expected because we had two first order systems, right? But just keep that in your mind, right? That that's what's happened. Okay, so we can continue to algebra this, right? And we will, because we're going to try to get a transfer function here. And we're going to try to get our transfer function. So let's continue our algebra. Come on, you can do it. All right, so if I multiply through by k over m on everything, right? I'll get this plus k b k m omega plus t sub l is equal to k m times e sub n, right? And so massage this just a little bit more. I'll multiply this through. All right, so I just multiplied through, pulled out my omegas. I'm left with this. Like I said, we can transfer function this, right? Our input is E in. Well, we got two inputs, right? We got E in and we got TL. Our output is omega, right? So we can once again create our transfer function. That's what we've got. That's our transfer function. It's gross and it's nasty, right? It's actually not that bad. It's actually not that bad. But it's second order. So now what? Now if I wanted the block diagram for this, right? What's my input, right? Remember, my input is still E in, right? That's the signal that I'm getting. But this is going to be multiplied by Km, right? Remember, I'm trying to recreate this as my input, U. This goes in to a summing junction. What's coming here? The load torque. What did I just make here? U. Let me use red so that it tracks back. What does U get multiplied by? That transfer function. What comes out? Omega. Notice No longer a feedback system when we do it this way. How do I know? Well, the signal doesn't get fed back at all, right? Okay. Is it that simple, right? So I said the pro to the previous one is I can get any signal off of that I want, right? This particular one, I can really only get omega. I really only track, I mean, I could track U, but it's not really that interesting, right? Not really that interesting to track our input, right? Because it's just our voltage that's being gained, right? So it's scaling our voltage up by some amount and then subtracting off some other constant, right? Which isn't super interesting. It's just going to be a flat line. Really, the only interesting signal here is omega. But what if you wanted to know about the current, right? How does the current response change inside of your circuit? You got to do it the other way. And so there's trade-offs, right? Computationally, this is going to be a faster system because there's fewer parts for it to calculate, right? Yeah, Danny. TL is just a load torque. Question was, what is TL? Yeah, it's just some constant, physically represents the whatever you have on your system to start with, right? Some initial condition based off of the machinery that you actually have to use. Okay. All right. So when we do things like Simulink, this is what we want in Simulink, right? Like I said, you can also identify a state space operator in Simulink if you like, right? Simulink will take both, but in general, when you look at Simulink, this is kind of what's happening. You guys have any questions? Okay. So you can do algebra to block diagrams, right? So you can, I want you guys to think about this is if you had a really complex system, if you had a really complex system set up as a block diagram, you would be able to collapse it just from the block diagram using algebraic manipulation, right? It's very important that you guys understand that there are multiple ways of solving block diagram problems, right? There's no one overall correct solution. You can do it multiple ways, right? So if you look at this system, v plus 7x is equal to f of t, you can rewrite that, right? You can rewrite that as x is equal to the integral of f of t plus 7x dt. And so we can draw a block diagram for that. Right? So notice what we did here, right? So that first one, block diagram A, is just for the system v plus 7x is equal to f of t. The second one is the integral of f of t minus 7x dt. Okay. They're the same system, but they have different look to them, right? They're the same system, but they have a different look to them. Right, so how do we get from one to the other, right? Well, it turns out that if we have series block diagram elements, you just multiply them together. Okay? So if you've got some transfer function T1 of S and some other transfer function T2 of S, and both of those are in series, multiply T1 and T2 together. Done. Now you get T1 of S times T2 of S. Right, this is going to allow us to collapse things that are in series into a single block, right? Which cleans up our block diagrams. Or if we have something in feedback, well, if you have something in feedback, you can use this equation for negative feedback. So if you have a system here where you've got a transfer function, and then you're feeding back through a second transfer function, h of s, right? The equivalent loop, it becomes one transfer function, g of s, divided by 1 plus g of s times h of s. notice, right, if we look down here on the diagram, we have defined signals A and B here, right? So why don't we prove this out a little bit, right? So if I'm looking at this figure C, right, I'm gonna put a square around it, this guy. And I've got A and B. Well, what is A of S? A of S is just F of S minus B of S, right? Because it's at that summing junction. It's whatever is coming out of that summing junction, we've got A minus or F minus B there. I can also write an equation for X of S here, right? X of S is equal to A of S times G of S, right? Because we've got A times G, and what comes out the other side is X. And finally, I can write an equation for B of S, which tells me that H of X times is X of S, right? So again, if we come down, we're just running the loop, right? And we're splitting it at the output of each of our blocks, right? We have X of S coming out of G, we've got B of S coming out of H, right? How did we get H? Well, H times X gives me B, right? We're just taking these separate parts, and look what we're gonna do. I'm gonna solve this to get F of S and X of S as the only variables that I have left, all right? So if I take this equation and I plug in A of S here, right? I'll get X of S is equal to F of S minus B of S, whole thing times G of S, right? And I can take that B of S equation and I can plug this in here. And if I do that, I get X of S is equal to F of S times G of S minus H of S times G of S times X of S. Okay, and I've run out of room. I don't know. Oh well. And group all of my X's together on one side, right? So let me do that all in one step, right? All I've done is I've moved my X of S terms over to one side and taken the X of S out, right? Because it would be X of S plus X of S times G of S times H of S. Okay. We got that equals F of S, G of S. And look, if I cross multiply everything, I'm left with that. Right? You can do this for any part of that system. You could make the transfer function for any signal that you want. You can. And that's fine. In certain cases, it might be beneficial or applicable, or in some cases, it might not. Okay. You guys have any questions on block diagram algebra? The big thing I want you to remember here, right, is this and the fact that if you have things in series, they don't get multiplied together. If you can keep track of your feedback loops and your things in series. And what we're trying to do, essentially, when we collapse these, is we want to handle the series elements first and try to make it look like the feedback loop that we have there, because then you know how to handle it. There are more than one correct block diagram that's possible for any given system, right? We've shown a couple different ways you can do this. It depends on what you're interested in. It depends on what variable you want to analyze. You want to analyze current, well then you better make sure that you have current out as a signal somewhere, right? You want velocity, you want pressure, right? That's what it's comes down to. All right, so let's try this one together, and then I'm gonna let you guys loose on one. I think. Yeah. Good. All right. So, man, draw a block diagram for the following equation. The output is x of s, and the inputs are f of s and g of s. So we got two inputs here, right? So before, we just kind of took both of those inputs and we took both of those inputs and we treated them as one total input, right? That's what we did. So let's start by making a transfer function, right? So I'll put my D operators in. You'll notice that I take the of t off when I'm doing these just because there's no real reason. If I want to make my transfer function, there's my transfer function. Yep. There it is. What if, for a second, they were like, you know what, I want you to find the transfer function in terms of f and the transfer function in terms of g, right? How would we do that? Well, it's a good question. It's a good aside here. Specifically, if I wanted the transfer function for x with respect to f of s, I would treat g as if it were 0. And I would just do it for the system where g of t is 0. So essentially, I would ignore one of the inputs, right? In that case, if I had x over f, right, as my transfer function, I'd end up with something that looks like this. And if I had g over f, where I ignored x, or I ignored f, try that one more time. That should be x over g. If I ignore f, and I leave f as 0, I end up with negative 4 over 5 d squared plus 3d plus 6. So what is the difference? Well, all I've done is, instead of treating 10f of t minus 4g of t as my total input, I'm picking one or the other. Is that legal? Is that fine? Yes. Why? Because with a transfer function, we are assuming very specifically that all initial conditions are 0 except for the input that we have. We want the relationship between an input and the output, not the other input. So we're assuming that both of these are independent inputs, okay? We'll come back to that idea later. As long as we can get to this transfer function for everything, that's what we need for our block diagram, right? Why is this what we need for our block diagram? Well, it's everything that we had before, right? I've got the transfer function. What goes into my transfer function? My input. Well, this is going to be my u. This is going to be my y signal, right? Okay, so if I need to construct that u signal, right? I need to construct u. Right, so I've got some signal here that I'm going to call u. That's going to come into my transfer function, right? This is going to come into my transfer function. And that's going to spit out my output, which is equal to x. But what was u? Right, u. U is the sum of 10 times f, and here's f of t, times 10, minus times g of t. That's our block diagram. You could draw this other ways too, right? You can break this down into the transfer function of x and the transfer function of g and draw the two transfer functions, see how they interplay, but we don't have to. The question sometimes arises, why don't you just put a -4 as your gain? Don't put a -4 as your gain. It doesn't make any sense to have a negative gain. It's an amplification. An amplification. If we're going to subtract it, we need to subtract it at the summing junction. Okay. I'm going to throw you guys into your team. You get 30 minutes to work on the next thing. All right, you get your breakout rooms and everything. Walk around, both in class and virtually. Okay. All right, so this is going to be time trials. We're double points since we didn't do anything last week. All right, you guys know the deal. You'll get 30 minutes to do this problem. Guess what? You get to draw the block diagram for the following model. The output x of s and the inputs are f of s and g of s. It's a two-part model, right? Oh, very exciting. All right. That should work. I think that's everybody. Options, 30 minutes. There you guys go. There was a question in the chat. What is it? More people?
Hello? Hello?
Yeah. What's up?
Finally. Sorry. Can you put me back into my breakout room? I mean, I never even went. My internet's been loading.
Should be
Huh?
able to get it, but there's only like 40 seconds left, so
Oh,
you're assigned.
I'm sorry. I've been trying this whole push and refresh this whole time. We started my internet too.
No worries.
Darn it. Are you going to go over the problem?
Yep, in a minute.
Perfect.
Three, two, 10 seconds before the breakout room drops. Whole internet collapses on itself. You don't want to be stuck in a breakout room when it collapses. No bueno. Okay. Seems like everybody's back. So what? What do we do? A couple people got it. A couple people got close. Right. So good stuff. Let me do this. You guys see my screen now? Everybody, hopefully.
Yeah.
Okay. So, what do we got? We start off with our x dot and our y dot equation. Now, the specific thing about this is it says to indicate the location of y of s in the diagram. Okay, and that is important because this is giving you a clue as to what we need, what form this diagram needs to take. Right, you need to have y of t in our case as some sort of output signal, right? And so if we take the x dot equation, right, we do our algebra and we get an expression for x of t. Right now, that's not the transfer function, Dr. D. You're right, it's not, right? I stopped short on the transfer function, right? Now, a couple people did this and ended up with a secondary feedback loop, which is not incorrect, right? But also not necessary. Also not necessary. I'm going to stop short on this transfer function as well. Hey, what's that 1 over d? What's special about 1 over d? Integrator, there it is. It's an integrator. Okay, so what? What do we do? What do we do from here? Well, we have everything that we actually need to write our block diagram, right? And actually, I would say that let's use red for this one and use blue for this one, right? So what do we got, right? Where do we want to start? Well, it doesn't really matter. We'll start with y. We'll start with the y of t side. Does it matter? No, it doesn't. You can start wherever you like. But I'm going to start with y of t. This y of t equation. Well, y of t is equal to what? It's equal to 10f minus 30 times x times 1 over d. Okay. So I know that I'm going to have f of t. This is getting multiplied by 10, right? This goes into my summing junction. Why? For later, right? Well, what do we know? I know that this has to be subtracted by 30x here, right? We'll leave that there for now. 30x of t. I know that. We don't know how we got it, but we know that it's there. This then goes into my, I used the wrong color, didn't I? Problem. Yeah. Change that so that we don't get this. This will be red. And this one will be green for reasons. Okay, so all I've done is I said, well, I have some transfer function 1 over d, right? What do I need to go in there? Well, I need 10 times f minus 30 times x. That's what I need to go into 1 over d, right? How do I get that? Well, it's a summing function. F times a gain of 10 minus 30 minus x times a gain of 30. I don't know where x is coming from yet, but I don't need it. So what does this give me out? Well, right, y of t. And that's the important part, right? Because the question specifically asked us to designate where is y of t. So if you put both of these equations together, you might potentially lose where y of t is, or y of x is. Potentially, depending on how you do it. This goes into a summing junction. With what? Well, y of t plus g of t. Well, where is he pulling this equation from? Great question. X of t is equal to my transfer function times y of t plus g of t. So now that I have y of t plus g of t, that goes into my transfer function there, which is going to kick out x of t. And guess what? That's where that came from. That's it. That's how we come about it. So what is that? What exactly are we doing? Right? Sometimes, what time is it? Perfect. Sometimes, I want you guys to look at this. Sometimes it's we can think about this in terms of this equation, right? One step ahead or one step before the transfer function, right? I don't know why I used blue. I should use green here. No, that's totally great. It looks great. Looks great. All right, so sometimes it's helpful to look at this equation, right? Why? Because it's telling me my output, y of t, has to be equal to these things, right? I know that the transfer function, I know what my inputs are. It's f and x to this, right? So I know that that part is my input. Right? Think about this. This is u, and this is g of t, which is, we're going to call it our time domain transfer. It's g of s, really. G of capital D, whatever you want to call it. Let's call it G of capital D. Right? Again, this equation here on the left is just U times H of capital D, right? Because my other transfer function is 1 over D plus 5. So I know that X has to equal this, right? Well, how do I get there? Well, the transfer function times my input, right? Transfer function times my input. It's always the transfer function times my output, right? And that's a really big and important idea that is going to come in real handy when it's going to come in real handy later in the semester when we start with Laplace transforms and the like. Does have any questions? Yeah, Sean. Yeah. Because it comes in as a negative on my summing junction. Right? So 30x is the green one. Oh, sorry, I drew it from the wrong spot. And I did draw that from the wrong spot. I apologize. Typically, it doesn't really matter, but typically this is the This is the notation that you would be looking at, right? So it's 30 times x. Yeah, sorry about that, guys. I drew that not from the x, even though it's the output of that, so it's still technically x anyway. But in practice, what you will see on Simulink is that transfer function has one input. For most systems, the transfer function has a single input, single output, right? What we're talking about. So, do we have any other questions on that problem? Everybody doing okay? So, if I gave you a block diagram, would you be able to obtain the transfer function? Well, the hope is yes, right? You can. Can you? Maybe right now we presently cannot, but hopefully we should be able to, right? The idea is that if you're given a block diagram, you should be able to obtain a transfer function. And in some of the ones that we've done so far, that seems pretty straightforward and reasonable because we have a single block, right? And we would just read the transfer function off of it, right? What if you're given something that is cluttered and complex and you just want a system-wide transfer function? Can we do that? Well, yes. Depends how. Well, it partly depends on the diagram and personal preference, right? You can always brute force these things into submission, right? But sometimes, sometimes you don't want to use a shotgun, you'd rather use a scalpel, right? Sometimes, use a lightsaber, which is a more elegant weapon for more civilized time, right? Except there's people still cutting each other's heads off. So I mean, is that really that civilized? Let's think about that. Anyway, maybe don't. Cool. All right. So what am I talking about? Let's run through this example. Hey, look what I've got here. This is a system that is. I want a single transfer function, right? I want the transfer function of x with respect to f. Okay, this is a feedback system. What should we do? Well, like I said, you can brute force this, right? What do I mean by brute force, right? Well, you go from each node, right? You say, well, z of s is equal to f minus 8 times x, right? You can do all that. Or we can combine the top two, right, together because they're in series, and then use our fancy feedback equation, right? But let's run through brute force real quick. So when I say brute force, what am I saying? Well, again, right? I'm at this node. Not this node. Okay. And if I look at that, z of s is equal to f of s minus 8 times x of s, right? Everybody's with me so far. Okay. I'm going to jump over to here, this point, where the blue is now, right? Okay. X of s, I can come up with an expression for x of s. Right, I just combine those things together, right? Because remember, they're in series. We can collapse in series together by multiplying them. We're left with this. I'm going to leave it in this form. Well, that's not entirely true. I'm going to rewrite this as x of s is equal to s plus 6. But I'm not going to combine these z of s. I'm going to leave these in the parentheses. I'm not going to expand them. All I've done is just, it should be, I switched my x and my z, didn't I? Yes, I did. Man, sorry. Let's try that again. we'll actually do the algebra correctly this time. Don't do the algebra like Dr. D does. Do it the right way, and you'll live a happy life. I'm pretty sure that's in a book somewhere. But anyway, right? So now I've got an expression for z of s in terms of x, right? And I'm going to plug that in here, right?
Why do you use z of s and not y of s?
Because you could do y of s, right? You could, but y of s just goes right into 1 over s plus 12, right? I presumably want the transfer function from my overall output to my overall input, right? So x of s, right? I'm trying to create x of s over f of s. So by the rules of block diagram algebra, these two being in series means that you just multiply them together. Danny. Does this system invert a lot of its own dynamics? So, I mean, think of it, so potentially it'll invert its own dynamics, but think about it less as that and more of like if this was your cruise control, right? And so, yeah. So yeah, we'll talk a little bit about that, right? What does this actually mean, right? The fact that f and x are being subtracted tells you a little bit, right? Tells you that they have to have the same units, right? Typically, this signal z of s is what we will call our error signal, right? In a typical feedback control, right? If this is your cruise control, you set some variable f being your speed at like 70, right? And x will read out your speed and tell you how close you are. And subtracting them, you want them to get to 0, right? You want 70 to be the output and 70 to be the input, right? And that will zero out the rest of it. But anyway, from this point, right, we plug these things in, we'll get an expression for f of s. Oh my gosh, I can hardly write my own notes today, guys. Right, so I get this. Now, why didn't I do the algebra to expand this, right? Because it doesn't buy me anything at this point. And in typical, like, in the add-on to this class, which is a feedback controls class, you want to be able to tell what your poles and zeros are. We'll talk about poles and zeros very shortly, in a very brief amount of time for very little time, because it doesn't really affect what we're doing, but that's kind of where this is going, right? And so if I make my transfer function now, right, I've got x over f, right? This is great, right? So that's my transfer function, so I can collapse this entire thing into a block that looks like this. And so that. Okay. Once again, you get a second order system. So what's the point, right? Well, the point is that if you're given a block diagram, you should be able to look at it, condense it, and simplify it, right? That's kind of the point. Kind of the point. Let's see something. Tell me to class until 12:15. All right, we're gonna go over. I'm gonna do another problem next class regarding this as recap. Don't worry. I'll do a real beefy one at the beginning of next class. That's so many algebras that people heads will turn. But this is important. I want to get to this today. Right? It's been a long time coming. The question was asked during time trials, right? What are these f of t's and g of t's? I don't like keeping functions in there. Well, first of all, we should keep the functions in there, right? Get comfortable with using the functions. But what do they represent? They actually represent our input functions. Okay. There are some standard input functions that we are going to cover extensively in this class, right? There are more than these, right? But these are the ones that are most typically used. Right? These are the ones that are most typically used. And in fact, the entire semester from exam 2 on is just how do we deal with sinusoidal inputs. So we're not even going to touch those for right now. We're going to dedicate a full like 3 weeks, 2 to 3 weeks, just to that, right? But right now, we're going to talk about some of these inputs, right? So we've got a step input. Everybody's heard of a step input before, right? Just instantaneously turns on and goes to a value. Step. A unit step is one that goes to 1, right? Where the value of the step is 1. Step input shows a sudden instantaneous change, right? The input function itself is 0 for t less than or equal to 0 and 1 for t greater than 0. Many times the step input is initially 0 and instantaneously goes up to a value. Right now, is this realistic? Does anything just automatically turn on? No. No, but things are very fast, right? And can be modeled approximately as a step. A step input with a magnitude of A is just the unit step times the magnitude A. Right? So you're going to see that the way that we define a lot of these inputs is we define them as the unit step or the unit ramp or the unit version, and then we just are multiplying by some constant to get to the next level, right? To get to wherever we need to be. And so that's a step, right? Everybody's seen a step before. Cool. We also have a ramp. A unit ramp is given by u of t is equal to t. A ramp input function increases linearly with time at a constant rate. If you have a unit ramp, this indicates to you that the slope of the function is 1. Right. In general, the ramp is u of t times a, where u of t is equal to a times t, where a is the slope of your 1. It can be positive, it can be negative, right, in any direction. Then we have a ramp step, right? So for those situations where an instantaneous step isn't going to cut it, right? It's not going to predict our dynamics quickly enough or accurately enough, I would say, not quickly enough. We can generate a ramp step, right? So we have a ramp that goes up until it reaches a certain level and that plateaus, right? And if you thought this is just going to look like the equation for a step plus the equation for a ramp, then yep, 100%. And so it's a ramp from 0 until some time, and then it's just A at that time. It's a more realistic representation of a step input, right? Something like a velocity profile would look like this, right? You're driving your car, you ramp up to 60 and then you hold something like that. Right, then we've got pulse or general square wave. Right? Pulse is a step function that turns off after a certain amount of time. Right, input has a constant magnitude over a finite interval, which is my pulse duration. and it's 0 before and after, right? So it turns on. In this case, our pulse input is 0 for time less than or equal to 0. At time equals 0, it then becomes A. There it bounces up to A for some time interval between 0 and T1. And then it's back to 0 for T greater than T1. This allows us to talk about an impulse. We can go from pulse to impulse. So what is an impulse? It's a very large force that lasts over a short duration. Danny. Yep. Think about when you hit a nail with a hammer. That is an impulse. You strike the nail with a large amount of force over a very short period of time, right? Another way of thinking about this mathematically is that if you took an impulse input and you treated it like a pulse function where the duration goes to 0 as in the limit as time goes to 0, right? So, okay, weird. So let's talk about this number, right? So suppose I have 150 newtons, right? And I apply it over a very short duration of 0.1 seconds, right? The pulse input, right? Goes up, on, turns off. Good. For 0.1 seconds. The strength of this, right? The strength is 15 Newton seconds. Okay. So it's 150 newtons times 0.1 seconds. So I've got 15 Newton seconds of strength here. And that is the area under my curve. That is the area under that pulse, right? So right. Right. That's what we're looking at. So therefore, the impulse input, right? So right. We talked about that, right? So that's my impulse, right? So what happens? I said if this happens, if we take the limit of this as time goes to 0, right? If I have to keep that amount of force constant, if I don't change my amount of force, but I change the amount of time that it happens over, right? What happens? Right? These two are equivalent, right? Why? Because I've cut it in half and I've increased the force, right? And so I can continue this trend over and over and over again until I get something that has near infinite magnitude and near infinitesimal amount of time, right? So mathematically, a unit impulse is represented by a Dirac delta function, delta of t, which has infinite magnitude but infinitesimally small time duration. And hence the area of the impulse is unity, right? Now this is a dirty trick, right? Because it's telling you that infinity divided by infinity is 1, right? Which not really. But what it's saying is that it's so we're considering this unit impulse to have strength of 1, but it's so large and it happens over such a small amount of time that it balances itself. So if we have a short duration impulse with the input of weight and a strength of 15 Newton seconds, the weight of the impulse is thus 15 times the Dirac delta. So if we have, again, just like the step, we're going to base everything off of our unit version of it, right? And then we're going to scale it accordingly, right? Why would you want to do that? Well, the reason that you want to do that is because in the Laplace transfers, the Laplace transforms, the Dirac delta is calculated for us, right? And then we have a sine wave, which we will go over ad nauseum, but let's talk about it right now, right? So it's a sinusoidal input function that's a repeating periodic input that can be represented by sine and or cosine functions, right? So if you see sinusoidal, doesn't mean just a sine wave, right? Cosine works just as well. A and B are the amplitudes, right? So in general, we can write our input here as u of t is equal to A sine omega t plus B cosine omega t, right? Because we can, as we'll find out, you can decompose things in the Laplace domain into sine and cosine via the Euler's theorem, right? So A and B are amplitudes, omega is the frequency. The frequency is sometimes expressed in cycles per second or hertz, right? So 2 pi radians per second is 1 hertz. Let me see something. Yeah. Okay, you guys have any questions on the standard input functions, right? We've got ramp, step, pulse, impulse, and sinusoid, right? So let's just talk a little bit about this. It's like 2 slides, and then we'll probably be done for today. But I don't think we're going to jump into the different cues stuff right now. So as of right now, we have covered modeling, the standard forms of systems, and system response via numerical simulation. Not really. That's what the book says, but the book does these chapters out of order, so we haven't really done that yet. Next, we need to determine the dynamic response of a linear system using analytical techniques. We will get to numerical solutions, right? But for some reason, the textbook put the simulate stuff before the analytical stuff, which I thought was weird, but they did it anyway. But I think it's better for us to get a sense of how to do it by hand. That way we know whether or not our simulate models are lying to us. Okay. So now we have to determine analytical solutions, right? So in particular, we need to investigate analytical system responses to our standard input functions, right? And specifically a step, a ramp, an impulse, or any combination of those, right? We're going to focus on solving simple first and second order ODEs by hand and using analytical methods. And finally, we will establish performance criteria for system response. And this is important. This is the important stuff, right? Whether or not I will stand by this. I personally believe, regardless of what career path you decide to go into in biomedical, mechanical, whatever engineering field you go into, understanding how to set system criteria and parameters is going to be the topic that is probably most used by anybody after this class. You might not ever model a system ever again, but if somebody asks you, hey, what's the settling time on that system, right? Or what's the natural frequency, things like that, those are terms that come up frequently, right? And things that you are going to want to understand if there's a conversation being had about it. Okay? So we'll talk about time to reach steady state, overshoot, damping, natural frequency, damn natural frequency, all manner of things. And specifically, how can we reverse engineer parameters given a system response, right? So if I have the system response, how do I figure out, what the spring constant and the damping constant are? System designers should understand the basic parameters governing first and second order system. How does resistance parameter affect my time to reach steady state? How does stiffness affect oscillation frequency, right? These things are not just coefficients, right? They are physical, they are tied to physical devices that will alter the response. Imagine for a second you were designing something, right? And you have determined that you need a spring with a spring constant of 2, right? 2 Newton per meter. But the manufacturer you're going through no longer makes 2 Newton per meter, and they're all out. You need to get this thing out to market. what do? You just halt production of your device, or do you go back to your model and figure out how is this going to affect my overall system response, and can I tweak some of my parameters to make it something that is regularly available, right? Oftentimes, the response for a complex system that's at higher order, like third or higher, can be broken down into first or second order response, or a series of first and second order responses. Turns out that a third order system is really just a combination of a second and a first order system when it comes to response. System designers, so the name of the game, right? The name of the trade-off game is model complexity versus model accuracy and time to obtain a solution. And that's the game here. How do we get a model that's good enough that's not going to cost me a ton of money in terms of computational research? Right? We definitely do not have time to wade into. Well, do we? Nah, we'll save it. Save it. You guys go early today. We'll save DiffEQs. Yeah. Okay. Thursday, we'll recap some of the block diagram stuff. Okay. We'll go over DiffEQs. We're going to go over first order system response. All right. We're going to go over a lot of different things. So that should keep us up and through. I think first order system response is where we're going to leave it this week, and then next week we end up in second order systems. Okay. I'll post homework. I'll post the homework today or tomorrow at some point, depending on if there one I can give back to my office. Okay.
Can you do office hours on Thursday since meetings have run over your office hours?
No, Dante, I have class during that time.
Shoot.
Thursday, I teach from 9:45 until 5 o'clock with a 15-minute break between this class and my next.
Dang.
So,
okay.
not a,
Thank you.
What would be the earliest you can have in the week? Because I know on Monday it's not. It usually is. It's at 9 to
11, yeah.
11, and then the latest would be 5, right? On like
Normally it's 3 to 5, probably.
yeah. I'm just trying to. Yeah. Only because then the only day would kind of work for me is Monday because
Well, here's the thing. If you have another day where you have a time that is easy for you, shoot me a message and I might be able to meet with you.
Okay.
It all depends on my schedule. Those are the largest chunks of free time that I have in my schedule.
Yeah. I think it's fine. It's just the struggle is the 9-hour difference. So like the 3 to 5 just doesn't work because that's midnight to 2 a.m. So Monday will work the best. So you'll probably see me on Monday for additional questions. But okay, thank you.
No problem.
Did your office hours change this week because of the capstone presentations?
They wanted faculty members to come to a bunch of them, so that's why I canceled yesterday. That's the only day that's going to be affected, though. So.
Okay. Yeah, I didn't see any message or like announcement that the rest of this week's office hours, but it was me, so. And yeah, anyways, my groups were presenting pretty early yesterday, so.
Yeah, just
Alrighty.
yesterday's were affected. The rest of the week's business as usual.
Yes, sir.